From the Riemann zeta function, in particular from the functional equation that we derive for the Riemann zeta function that we can now use also for s less than 1, or the real part of s less than 1 in particular, if you want to think about s as a complex number. But now I'm going to calculate zeta of minus 3 by using the equation that we derived here. In particular, we will calculate this expression for s equal to minus 3. We will evaluate it at s equal to minus 3. And what we get is, if we set s equal to minus 3, we get gamma of minus 3 over 2 times zeta of minus 3 times pi to the power 3 over 2, and then on the right, so let me rewrite it properly, 3 over 2. On the right, we have gamma of 1 minus minus 3, which is 4, divided by 2, so we get 2, gamma of 2 times zeta of 4, and then we get pi to the power minus 2 here. So this is the equation that we get. Now for zeta of 4, we have a formula for this one, because we know that in this case, since s is equal to, in this case the argument of zeta is equal to 4, so we can use the summation 1 over n to the power 4, and we have to sum from 1 to infinity. This is a very recurrent summation. It also arises, for example, in quantum mechanics, and you can use a Fourier series to evaluate this kind of summation. I have already evaluated it in some other videos, some other courses, but I don't want to do it now. It is possible to do that quite easily, and the result of this is pi to the power 4 divided by 90. Then we have gamma of 2, and that's a very simple one to calculate. Gamma of 2 is equal to 1, because we have a property for the gamma function, in particular gamma of some integer, let's call it n plus 1. Well, this is equal to n factorial. It's very easy to calculate from the definition of the gamma function. One simple way of doing that is by considering gamma of z plus 1, which is by definition equal to the integral from 0 to infinity of t to the power z times e to the minus t dt, and this is equal to, if you integrate by parts, you can rewrite this as minus t to the power z e to the minus t evaluated between 0 and infinity, and it's easy to check that this is equal to 0. Then we get plus integral from 0 to infinity of z times t to the power z minus 1 e to the minus t dt. But this is simply equal to z times gamma of z, right? Now I really want to use this property to find the value for gamma of minus 3 over 2, which is less intuitive, right? So gamma of minus 3 over 2 can be obtained in the following way. So in particular, we can write gamma of, we have minus 3 over 2 plus 1 here, and then we divide by minus 3 over 2. I have simply used this formula here by rewriting it as gamma of z equal to gamma of z plus 1 divided by z. Then, if we use it again one more time, we can rewrite this as gamma of minus 3 halves plus 2 divided by minus 3 halves minus 3 halves plus 1. And this is simply equal to 4 over 3 gamma of 1 over 2. Now it is simpler to calculate gamma of 1 over 2 because gamma of 1 over 2 by definition is integral from 0 to infinity x to the power 1 over 2 minus 1 times e to the minus x dx, and this is equal to integral from 0 to infinity e to the minus x over the square root of x dx. And now you can change the variable here. You can go to the square root to, you can go from square root of x to t. So this is the substitution that you are going to make. And it means that dx over the square root of x is equal to 2 times dt. And this will become integral from 0 to infinity e to the minus t squared times 2 dt. And this is simply equal to twice square root of pi over 2. So this is just square root of pi. Simple as that. So now, all in all, when we substitute the results here, we simply have 4 over 3 times square root of pi, which is a gamma of minus 3 halves. Then you get zeta of minus 3 pi to the power 3 halves equal to gamma of 2, which is 1, zeta of 4, which is pi to the 4th power divided by 90 times pi to the minus 2. Now you can see that all the pi's will cancel, so you are left with zeta of minus 3 equal to 3 divided by 90 times 4. So it's 1 over 4 times 30, which is 1 over 120. Exactly what we expected. And this is an important result because it gives more intuition behind the Riemann zeta function.